Hi guys. Right, today, as the title suggests, I want to talk about earth leakage detection, and what I'm hoping to do from this video is to create a DIY detector that you can use to measure the earth leakage on appliances. So what I'll do is I'll first of all just explain a little bit about what earth leakage is. So earth leakage is something which you hear quite a lot in domestic environments. The houses, well, where I live in the UK, most houses have what's called an RCD, or there are different makes of different types, different makes of RCD. And what that does is, if there's any earth leakage, it's meant to cut the power at the fuse box. So you would need to go down and reset that. Now, a lot of the times you don't know what it is that's caused that problem, which is where hopefully this detector will come in. Like I said, there are detectors available that you can buy, but they're more professional items and they're very expensive. So I'm thinking of trying to put something together that will at least detect whether there is some earth leakage there or not, just to help identify perhaps a device that's causing a problem in the house and you're not sure which one it is. So first of all, let's just show you what earth leakage is. So if we have a device, let's just draw a box for a device here. That's our appliance, okay. And this could be any appliance that you plug into the home. So it could be, more often than not, earth leakage occurs on devices that are prone to damp or can get wet. So things like hair dryers, steam irons, kettles, especially kettles, things like that, things that have got liquid in, because what happens is the liquid in the machine can sometimes ingress into the electronics over time when it fails or the plastic becomes brittle, seals fail, and that moisture will get into the electronics, and it's that sort of wet electronics inside that's where the earth leakage can occur. So let's just get some different colours here. So if we have our three lines coming in, we've got our live, and this is mains voltage. So in the UK it's 240 volts, and then we have our neutral line, and then we have our earth. Okay, so the way that current works, what should happen in a correct appliance is that all of the current coming in, so I'll just I'll mark that as an A, current coming in should equal the current coming out on the neutral line, and there shouldn't be any current happening on the earth line. So in a working machine here, we've got current coming in, say 3 amps or whatever it is, and then we should see that same current coming back out. So it's a current loop. That's the way that works. And inside the appliance, whatever this may be, motor or whatever, that current should just go through the electronics and be seen coming out on the neutral line. Now what happens when you have some earth leakage is that instead of this being a closed loop, we have a little bit of current. So I'll mark that as just a dotted line, comes out and leaks somewhere else. Now more often than not, it leaks to the earth line like this. So now in the case of this, we have the majority of the current flowing in this loop here through the live neutral, but we also have a little bit of current branching off and ending up on the earth line. So in this case, the current going in does not equal the current coming out on the on the neutral line. There is a little bit less because it's split off here, and that's what the earth leakage is. What we're trying to detect is what the difference is between current in and current out. And if there's some leakage, then we know that it's something has happened in here. Now, another way that you could have earth leakage is through a person touching that appliance. So if you have some metal on the outside of this appliance, let's say a screw. So say there's a screw on that appliance, a metal screw, and it's wet inside the appliance, and so there's moisture between the back of this screw or whatever metal is on the outside of the appliance and the live terminals inside. Then if you were to touch that, let's have our guy there. If we were to touch that, then the earth leakage then would come through here this way, through the screw, through the person, and to ground basically. So there's earth there, and it would come through this way. So two ways that earth leakage can occur. One is internally in the device through the earth lead, and the other way is through the person. Now that's what the RCD fuses are meant to protect. It's meant to stop this person getting electrocuted, and the way that that works is that it monitors the inbound current here on the live and what's received on the neutral, and if it receives a certain amount of difference between those two, so if there's a little bit of leakage here and it detects it, it cuts the power off. And that's meant to happen before this guy gets to feel that shock. And it's typically it's 30 milliamps is the detection before the fuse will trip. Now, the problem is in most homes that it's changing now, where you have individual detectors on each different circuit, but in most homes, mine included, there's only one of these RCD detectors for the whole of the house. So if this faulty appliance is plugged in somewhere, and it doesn't necessarily need to be turned on either, just plugged in, the RCD could be tripping every now and then, and nobody knows where that appliance is. So it's a question of going around the house, unplugging all your appliances, seeing if it happens. But if it's intermittent, again, it's difficult to trace. So you could have maybe 3 devices, and each of those have a 10 milliamp earth leakage. But combined, when they're all plugged in, you get the 30 milliamps or more, and it'll trip the system. So what I'm hoping to do is to create a device here which we can individually plug our appliances into and check them out. So if we were suspicious of a device, a kettle, steam iron, whatever, we could plug that in and measure the earth leakage. So what I was thinking was to get some sort of project box, and we would have our mains coming in, the feed. Maybe, I don't know whether it's just going to be a cable coming into here, or whether we could have maybe an IEC connector, something like that. And then either another cable coming out with a mains plug on it, a mains socket on there to plug the appliance into, or what I might do is just fit the plug directly onto that case. So it's going to be a UK 3-pin plug there on that case. And then inside, we've got our mains coming in, so we've got our neutral and our live and the earth. And then also on this case somewhere we will have our display, whatever that may be. It's probably a 7-segment display. Okay, so all we need to do then is measure the difference in current between these two lines. Now the easiest way to do that is to detect them both together. Let me just quickly draw the lines here. So if we've got live, earth, neutral. So what I'm thinking is to use a current transformer. You may have seen those. I've got some here, just 1 second. So I had these just knocking around. I've never used them, but these are current transformers, And the way these work is you put your conductor through the center of here, and there'll be a voltage generated on these when a current flows through it, because it's a transformer. These are 2000 to 1 turns, so the 1 is the single conductor through the middle, and there's 2000 turns on that transformer. And I haven't tried any of these yet. This is just a thought process at the minute. I'm going to have to do some testing with these to see what sort of output these generate when there's a cable through there with a current on it. But this is what I'm talking about when I say a current transformer. So if I was to put the current transformer around any one of these wires individually, there for instance, I could detect the current on that line. And if I put a current transformer on there, I could detect the current on that line. But then I'd have to take one away from the other and work that out and put it onto a display. So what I am thinking is, if I put both of these lines, not the earth, but if I put the neutral and the live through a current transformer and measured the voltage off that, and we're probably talking millivolts, then this should give me a reading on a voltmeter if there's a difference between these two. Because both together, if the input matches the output, there won't be any imbalance. It won't detect any current. But if the input is greater than the neutral output, then there will be a difference, and we will see a voltage generated in that coil. I mean, to further enhance this, we could actually have 3 detections. We could have one on each core here, so we could show the current on the live, current on the neutral, and the current on the earth. And we could also have this one as well, but it's getting a little bit complicated. All I'm interested really is this value here. It's the difference between the two. I'm not really worried about where this earth leakage is going, whether it's down the earth line or whether it's somewhere else, but all I'm interested in is if there's a difference. And then what I'll have to do is try and calibrate. Ideally, I want to end up with something that reads milliamps, so that when it gets to 30 milliamps, I know that it's that device is likely to trip the system. So this is what I'm proposing, and as I said, this is just the intro. I'm going to make another video after this. I might just add it onto this one, but it's going to show hopefully the creation of this. So like I said, I've got these current transformers. I've got a few of these, so I'm going to check those out. I have a bunch of these panel meters, which are voltage panel meters. Now I think they're all the same. They are. I mean, they look different to the back. They're just cheap Chinese meters that you can get them for a few pounds. But this one has a chart on the back and says it can be set for 2 volts full scale deflection or 20 volts. So I don't think this is going to be sensitive enough, because 2 volt full scale deflection is going to be 1.999 volts. So I don't think that's going to be sensitive enough. I think really I need something that's going to be about 200 millivolts full scale deflection. So yeah, I may need to change those. Again, I'll try it. I can connect it up to a meter and we can try this. This is the box that I had in my stock, so I was just perhaps going to use this. I may change my mind. Just a project box, and then perhaps put on the main socket something like this, maybe there, and that would then leave some room for a display or maybe an analog needle. I'm not sure how that's going to look yet, but that is the thing that I've got in mind. So I'll set up some tests, and then I'll come back and we'll continue the video. Okay, so just continuing on from the video. I've just constructed this makeshift test lead here. So all we've got here is the mains plug, mains coming in. I've separated out the three conductors, the live, the neutral and the earth, and then they just go to this socket here so we can plug in a test device. And what I've done is I put a current transformer on each of the individual lines. Again, this is just to test, just so we can figure out what sort of meters and things we need. But I put one on each line, plus I have the one from the combined lines. So if I just show you the diagram I did. So we've got one current transformer on each of the lines, and then this one here is the combined one, and this is probably the one that I'm going to use in the final product, where I'm determining the difference between those two lines. Any difference in current is going to show up on that output as the output on the coil. So that's the one here. So let's give this a try. Like I said, I've not got any earth leakage to detect at the moment, so I'm not going to expect any earth leakage, but we'll be able to see what we get from these lines in terms of voltage. So I'll plug that in. I've got a little PC power supply here that I can use just to power something onto it. Okay, we'll just turn that off for the moment. And let's just bring this voltmeter in. So first of all, let's put it onto the live cable. So this is the current transformer on the live conductor. We'll switch this to millivolts, which is the smallest setting that we can have on the volts. I suspect that is the one we need. And then we'll turn on this power supply here. Now this power supply is, let's have a look. It's rated, it doesn't say what the current is that it draws, but it's a 100-watt power supply, so it's not going to draw that much current, but hopefully we can detect something. Okay, so we'll put this on. This is on the live conductor. Okay, that's actually going over range. That it's fluctuating a bit, but it's, yeah, so just knock it down a range. Yeah, it's peaking over 200 millivolts, which is why it's going over range. It's fluctuating quite a lot. I expect that's because of the electronics in here that's doing that, but that shouldn't affect our end product. It doesn't matter really what current is being drawn by the load. The earth leakage is all we're interested in. If it's drawing 13 amps or it's drawing half an amp, doesn't matter. It's the earth leakage amount that we're concerned about. So if I change this now to the twin conductors, so the one that's measuring the current on the live and the neutral, I'm expecting it to show 0 because the input current is matching the output current, unless there is some earth leakage on this power supply that I don't know about, but I'm expecting it not to be. So disconnect that, and we'll go on to the combined current transformer. Yeah, 0. So in a working appliance, this is what I'd expect. Working appliance, the input current is going straight in and straight out, so it's a closed loop. This earth leakage isn't taking place, so the difference between these, or the current drawn overall between these conductors, is coming back as 0. So I think this can be the basis of it. I think we'll use the combined one like this, and then we can detect if there's any current coming off this. Now, this is going to be quite a small amount. As you saw, it was only perhaps 200 milliamps with this, the total current being drawn. These current transformers were detecting 200 milliamps. So, sorry, 200 millivolts. So what I'm going to do is I'll have to do some more testing. We'll perhaps get, we could simulate earth leakage by putting some resistors, high value resistors, between the conductor and the earth wire. So maybe I'll do that, maybe I'll set that up, and we'll come back and we'll have a look. I'll also make the box as well. I'll get on with that. I'll put the socket in the box and get a display. I haven't got the displays yet. The only ones I've got are the 2 volt full scale deflection, so I think I'm going to need 200 milliamps full scale deflection, because although this was going over range, it was detecting the full current of the live cable. So the earth leakage, I'm only detecting 30 milliamps on there, up to 30 milliamps. So I think the 200 millivolt range is going to be fine. So we'll test it with this first, but yeah, I'll get all that set up, and I'll come back to the video. So I just thought I'd show you this progress so far. All I've done is put the main socket into that box. I'm going to replace this cable with, I've got some slightly thicker cable here. This is 13 amp cable. And I've ordered some connectors for the end, so that's just so I don't need to worry about the current that's being drawn through these appliances. I didn't want to put some thin cable inside, especially as most of the time the devices that you're going to be collecting this are going to be things like hair dryers and irons and kettles, things that do draw quite a bit of current. So yeah, that's the progress so far. I've ordered another meter, a millivolt meter. So when that arrives, we'll put that in, and we'll continue the video. So what I have here is a test cable I've made up, and what this is going to be able to do is to allow me to generate an example of earth leakage. So the way I'm going to do that, this is going into the main socket. We've got live and neutral and earth. The live and neutral, we don't actually need the neutral for this test. What is going to happen here is the earth and neutral come past my current transformer, so this is how it's going to be in my test box, with the earth leads separate, and that way any current that comes back through the earth leakage, is not picked up by this current transformer, and therefore it will show the difference between what's returning on the neutral and what isn't, essentially, is what's coming through back through this earth lead. So this test here, what I'm going to do is I'm just going to put the earth to live via a suitable resistor, and that is going to generate a current back through the earth lead, and the current will come through the live and back through the earth, and this current transformer is going to pick that up. It's going to detect that, and we'll see an AC voltage on this secondary of the current transformer. The primary, of course, is being the conductor that's through the center. So I don't want this current to be too high, because it's going to trip my my consumer unit here, my fuse box. It's got the RCD built in there, which trips at around 30 milliamps. So I don't want this to be more than 30 milliamps for my testing here. So what resistor do I need? Well, I've got a couple of values. I've got a 22k value resistor here. This is a 5 watt, I think. Yeah, 5 watt 22k resistor. So 240 volts, which is the mains voltage here, divided by 22,000 is just under 11 milliamps. So that's a good value. I've got another one here, 12k. So that's going to be a higher current. 240 divided by 12,000. That's 20 milliamps. So both of these should work. What I might do is put them in series as well. So I'll end up then with 34k. So what does that give me? 240 divided by 34. That's 7 milliamps. So let's try the 22k to start with, and let's see what we get. I'll just connect up the meter and then I'll resume the video. So I've hooked my meter up to the current transformer and I've connected it to 5 volt power supply. I'll just turn that on. So this should read 0 or pretty much. These are, as I said before, these are only cheap meters, so I'm not expecting the accuracy to be all that good. I've hooked up my scope here so I can see the output from the current transformer as well. And these mains leads here, these are plugged in via that mains plug into the wall socket. So we've got our earth lead, we've got our live, and we've got our neutral. I've hooked up the 22k resistor into the live. So now what will happen is when I connect the earth to this resistor, we should see that current, which we worked out before to be just on 11 milliamps, will flow through this resistor. We're seeing 54 millivolts on the display there, 54.5 millivolts. And I don't know if you can see this one, but this is showing 52 millivolts RMS. So pretty much the same. You can see obviously the AC waveform there. It's saying 50 Hertz, which is what the mains frequency is. So I know that from our calculation that flowing through here is 11 milliamps of current, earth leakage current, through the earth line. What I need to do is try and calibrate this. I mean, what I could do is just say, okay, I know that 11 milliamps is 54 on the display, but it'd be nice if we could get that dialed in so we can see the actual, have milliamps reading on this display. So what I might do is I'll experiment with a couple of resistors, perhaps a variable resistor, either in series or parallel with this current transformer, and see if we can adjust this display to match what we know is flowing through here. So yeah, so this is 11 milliamps, and it's showing 54 millivolts, 54.6 millivolts on the display. So what I'm going to do is I'll get some resistors and just experiment with that and see if I can get that display to be a little closer to what we think the current is. So I've tried a few different variable resistors. The 47k appears to be getting me the best control over this. So if I touch the earth onto that resistor again, you'll see my display now is showing it's still millivolts, of course, but what we're trying to do is match this to the current that we're drawing. So at the moment we know we're drawing 11 milliamps, and the display is reading the same pretty much. It's quite sensitive, this pot, so as you can see I've got a lot of control over that. If I try and get this as close to 11 as possible, okay, 10.8, 10.9, that's close enough, I think. So now we know that that variable resistor is set to a value which works for us. I've disconnected the current transformer and we'll just check what value that resistor is at the moment. $2.2K. So if I replace this and put in a 2.2K resistor into my finished project, that should show us the correct reading. Now what I'd like to do is just check that value again with a different current value. So this one is 22K and is producing just under 11 milliamps. If I now add in another resistor, so this 12K resistor, and as we calculated before, that's going to give us a current draw of around 7 milliamps. So if we use that resistor, and we'll see if it's still reading a correct value. So I'll connect these together and we'll run that test again. Okay, so on here we were drawing 11 milliamps. I may have just knocked that resistor slightly. I'll just tune that a little bit. Okay, 11.1. And on this setting we should see 7. 6.8. You know, it's close enough. 6.9, 6.8. I'm happy with that. So if we implement this into our project with the 2.2K resistor, then this meter, the 200 millivolt full-scale deflection meter, should show us, represent what we're drawing in milliamps on the earth leakage, which is exactly what we want. We want this project to show us ideally how many milliamps are being dropped due to earth leakage. So that's good. The next part of the project is me going to be putting this into the box. So this is my box here, as you've seen before. I've got some connectors which I'm going to put into the end of the box. I have a mains cable I can plug in, and then our test device will plug into the top there. And as I said, I'm going to put this meter into the top of the box there. So what I'll do is I'll get all that fitted in, and then I will come back. I also need to buy a 5-volt power supply to go in here, just a small one. Maybe use a USB power supply, and that's to power this meter. So this is a 5-volt meter. So let me get all that together and get that ready, and I will recommence the video. So this is the finished item. Got the socket back on there, got the meter put in, and we've got a socket at the back for the mains input. I haven't put the back on yet, so you can take a look inside. We've got a small 5-volt power supply there which powers the meter. Obviously the meter at the bottom there. These are the live and neutral which come in and pass through the current transformer. And that's pretty much it. I've got the parallel resistors in there. I went for two 1.2K in the end, so it's almost, I measured it and it's almost 2.4K for those two resistors. They're in series, the resistors, but in parallel with the current transformer. And yeah, that seemed to give me a reasonable output, as we saw before. So let me show you this working. I can't find the lid for it, but I have got the lid that screws onto the bottom, so I'm going to screw that on, put some feet on it, and that'll be a complete. I did scuff this up a bit when I was cutting the hole out for the meter. I didn't notice the drill was touching it, so it's that's what those scuffs are there, but I'm not too bothered. So let's plug in the mains input. And it reads 0. And we'll connect up the test lead that we had earlier. So this is the same one. We've got the 22K resistor, which should produce about 11 milliamps of current draw. And we've got the 12K resistor, so when they're in series together, this one will draw about 7 milliamps. So let's plug it in. And what we need to do is just touch the earth wire to these two taps. So we'll switch on. Notice at the moment it's reading 0. There's no current draw. Let's have the end one. It's reading 7. Like I said before, it's 7 millivolts because this is a millivoltmeter, but with those resistors in place, this is pretty much matching what the current draw is in milliamps. And then the center tap there. Will draw the higher amount. So if we plug something in which doesn't have an earth leakage, or shouldn't do, this is just an LED light, so let's try that. So the unit's on, but no current draw, which is as it should be in a working device. So yeah, this is it's been a successful project. I can now plug in other devices around the home, so things that are susceptible to earth leakage are things like hair dryers, electric irons, electric kettles, anything really which has the possibility of getting damp or moisture or water around it. Even if it's in a damp environment, you can get earth leakage. So this device is useful because if something is failing in the house, if your RCD, residual current detection, is tripping and you're not sure what it is, usual method is you unplug everything, go and try it again, plug some things back in, try it again until you find out which item it is. Now with this device, you can go around the house and plug in all of your items into here and look at what the earth leakage is. If it's something over 30 milliamps, then yes, it's definitely going to trip. Or even if it's close to 30 milliamps, if this was reading 10 on a device, you had another device which is reading 10 or 15, then in combination of the two, you could find that that is causing the trip. So yeah, I've not seen anything quite like this before. I know that there are current detections. You can have clamp meters. You've got to sort of open up the cables and clamp just the one, the cables without the earth cable. But yeah, I think this has been a successful project, and I hope you've enjoyed watching it. If you've got any questions, let me know in the comments below. See you next time.